Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to the next lecture in this particular course on analytical, spectral and microscopy studies of inorganic compounds and nanomaterials. In the previous class, we have been looking at the ESR, EPR related aspects. We already prepared a base for that, all the details corresponding. Now, we will look at how to understand a spectrum, what kind of signatures are seen in the spectrum. Then we will go, once we finish that, we will go into a lot of application orientations of all that. Okay, so one of the things that we need to look at in order to understand the signature pattern is that the electron, I mentioned in the previous class, the electron spin coupling with those of the neighbor nuclei magnetic momentum if the I is non-zero. So that is one which gives a absolute spectral signature. So for example, if you have an unpaired electron connected with another, suppose say that there is a metal ion connected with a ligand. Let's look at that. I have, let's say, a metal ion connected to a ligand system. So where the n has got the I is equal to 1. Okay. So, and so therefore this particular unpaired electron can couple with this I is equal to 1. So this is nothing but, so electron, what you are looking at, the nuclear spin coupling. So this is the one which gives one of the signatures of this. Okay. So and also the electron that is belonging to a particular metal. So each metal has a different kind of I value. So even that also gives. So one is the hyperfine, other is the super hyperfine coupling. These are referred as the hyperfine and super hyperfine coupling. So let us. So that means if you have an unpaired electron which is connected to atoms like 1H or 13C or 14N, 31P, vanadium 51, copper, many others. It is not just only these 5 or 6, perhaps the most important source of chemical information in EPR. Reason is because of this hyperfine interaction in that. Okay. So one is that one. So this gives you the hyperfine interaction that you have. So this has got 2 contributions, and this is the isotropic kind of a thing and the anisotropic component. So these are the ones which actually gives information a lot about where the electron is present, as well as the molecular structural aspect of it. Okay. So now you have the electron and you have the nucleus, and so what is required is this electron density of this unpaired electron, whatever you are looking at for the EPR, its density felt at that nucleus in terms of the s orbital character. Okay. So that means you need to see the electron presence in that unpaired electron that is present, whether that particular orbital has any kind of a s character. So therefore that s character is the one which is felt at the neighbor nucleus, and thereby these two, the electron nuclear coupling, will exist. So the greater this s character at the nucleus, the greater is the coupling. So therefore this coupling value they will be dependent on the extent of this electron that is being. So if you have most often you have orbitals which are combined, they will have some level of s character will always be there, and that S character is felt at that. So, for example, you can see spins normally found in that radicals, the for example, or d and f orbitals, transition metal lanthanides, etc. So, all of these will have those electrons belonging to these will have some s electron density at the nucleus. So, therefore, and that the mechanism by which this is being transferred, that will decide the strength of the coupling interaction. So this is what this says: the spin orientation of the unpaired electron in the PDF orbitals to the inner s orbitals, and that is what is felt at the neighbor nucleus. So it is the s character at the nucleus of the neighbor which is connected. Okay, that is what decides. So this hyperfine coupling is shown as A value. So if it is A, then A iso, A aniso. Okay. So I hope you got now the point that the unpaired electron density, this unpaired electron density is felt at the nucleus of the atom that is associated with it, either directly or neighbor, like a ligand. For example, a metal and the ligand is nitrogen, nitrogen I value is 1. So the unpaired electron that is present at the metal, how the s electron density felt at that atom will show the coupling of it. That means you will have a better spin polarization of the electron density at the nucleus. So these values will allow one to basically understand the spin delocalization, one to understand the molecular structure, etc., and therefore we can understand the structural aspects as a whole for the system. Okay, whatever I mentioned partly earlier and partly in this class, let us look at through the diagrammatic. I draw your attention to this particular slide in the bottom left. In the absence of any external field, the electron spins of alpha and beta will have the similar energy. Kindly look at the plot that I am showing. So they have the same energy, but now when you bring this kind of a system into a magnetic field, or you take a magnetic field and put on top of that such a molecular system, what happens is the beta spin and the alpha spin are separated by an energy gap which is half g beta h, which I have already mentioned in the previous class of that. Okay, so these kind of things. Now what we are looking here is the neighbor nuclei coupling. So come to the right end of this. So the direct ms minus half to plus half, this transition shows the one single, but each of this will have a different ml values. So the coupling of these will come with the ml values. So ml will be 1 and 0 and minus 1, and for the other term also minus 1, 0, plus 1. Now you have one transition and the second transition and the third transition. Okay, so that is delta ml should be 0. So 1 to 1, that will be 0, 0 to 0 is 0, minus 1 to minus 1 is 0. So therefore you have delta ml should be 0. So that is what the transition allowed rule is. So you can see that. So you can see essentially 3 lines instead of 1 line. So you are supposed to have the 1 line here, but you find a 3 lines spectrum here. We are showing all in the derivative curve. Okay, so this is where we are looking at. So this is because of the electron nuclear spin coupling. So it's also called the hyperfine. So if it is the same, if the electron is also present in the same nucleus, then hyperfine. If it is present at the atom that is connected to that, then super hyperfine interactions. You can see that measure the difference between these things and calculate your A value out of this. Okay, I hope that you understand how this one single transition is now converted into multiple transitions because of the nuclear spin coupling. Now to understand whatever I said in the previous slide, now we have a set of values, set of isotopes or atoms and isotopes, and their spin value and their abundance value, and that should tell us which one will give coupling, which one will not give coupling. If the spin value is 0, then it will not couple, and those which are non-zero, they will be coupling in the fashion that 2n I plus 1. So I is that the nuclear spin value. Okay, for example, point number 1. Next is you need to look at the abundance part of it. We'll look at that. For example, hydrogen has got both 1 and 2. 1 is having a I is equal to half, 2 is having a I is equal to 1. So both are supposed to couple, but you see that the abundance of the deuterium is 0.015, whereas the abundance of the hydrogen is 99.985. So therefore you can absolutely forget, you can absolutely ignore the value of this such a low value, so that you can say only the H hydrogen, not the deuterium coupling to be considered with the electron. So electron with the 1H, not electron with the D or deuterium or 2H. Electron with 2H is 0, you can take it as electron with H is the maximum whatever you have. Similarly, if you take carbon 12, its I value is 0, so there is no question. Carbon 13, I value is half, but its percentage is only 1.07. Generally in most of the spectra you will not find coupling of that, unless you enrich the whole molecule with at least 50% of the carbon 30 or 20% of the carbon 13 or higher, then you will get 20% here. So that you can see a reasonably well kind of a value. So I again draw your attention to see at the table, because I am explaining the table with respect to that. So in case if you take now you understand, when you take the carbon 12, which is a 99%, can be ignored. Carbon 13 is only 1%, can be considered, should be considered, but 1% out of the 100 you will not be able to see the signals much. So if you make it 20% enrichment of the carbon 13 or so, or above 10%, you can start seeing the coupling for that. Otherwise you will not see the coupling for that. That's why many of the cases they will use a carbon 13 labeled material and then correspondingly look at the signals. Now come to the nitrogen 14, 15. So 14 has got nitrogen is I is equal to 1, 99.6, that is the maximum, and 15 is I is equal to half. This is also supposed to couple, but its value is so little abundance you will not see the corresponding coupling values. So essentially for nitrogen you will see only 1, for carbon you will not see anything except you enrich with 13. Hydrogen you will see with only 1 unless you deuterate it, same thing. Oxygen 16 and 18 have got I is equal to 0, 17 has got I is equal to 5 by 2, that should couple, but if you see the abundance, such a low abundance, you can completely ignore. That means if any oxygen ligand is bonded to your metal, you can forget about the nuclear hyperfine coming from that. But when you have a nitrogen associated or connected to your metal like that, so the metal with the nitrogen, the metal with the oxygen, so the oxygen case you can completely forget, no hyperfine, but nitrogen yes hyperfine, and this is I is equal to 1, and this is more than 99% of abundance is there. So therefore it is should be considered. If you take fluorine, it's 100%, 19 half could be considered, and phosphorus yes 31 with a half should be considered. And when you come to the sulfur, 32 and 34 have nuclear spin 0, not to consider. 33 has a nuclear spin of 3/2, should be considered, but you will not consider because its value is only less than 1%. So unless you make 33 labeled sulfur, you don't need to. So if I have a metal attached with sulfur also you can. So therefore oxygen ligands, sulfur ligands, you can happily forget about the nuclear spin coupling, or in other words hyperfine coupling, but you cannot forget with the nitrogen coupling. So I hope this is understandable. Now the rest of the table I am sure you will be able to understand. Among the chlorine you have two isotopes 35 and 37, both are 3/2. One is 75%, other is 24%, 76 and 24. Both are considered, both are important. When you have a chlorine you get an extra signature lines, the two sets of lines, one is coming from the 35 Cl, other is coming from the 37 Cl. Okay, so you can get these two, and in the EPR you will not see the two different things, but together you will find. But if it is a mass spectrum, then you will see the two different isotopes there. The arsenic 3/2, nothing is written, that means 100%, and selenium not all other, only 77, 7.63. There is some possibility of seeing the coupling with the selenium because it's 7.6. Now you go to bromine 79 and 81, so 3 by 2 50 point something, and 81 bromine 3 by 2 49 point. Again, just like chlorine, you get again together is 100%, and so bromine 100% you can take the nuclear hyperfine coupling, and chlorine you can take nuclear hyperfine coupling values. You should take the iodine again, yes, 5/2. So you have to take the corresponding nuclear spin and apply in this particular thing. So how many such nuclei are there in this? So you will understand this more when we come and explain as we keep going across. So vanadium, for example, 50, 51. So both have got spin value, but the 50 has 0.25. You can fully ignore, and the vanadium 51 has got 7/2, 99.75. It's almost equal to 100%. So fully. So in case of vanadium, you need to consider only 51, but not the 50. Okay, manganese 55, then iron only 57, cobalt 59, nickel 61. Other nuclei will not couple. And if you see the iron 57, still its value is only 2%. No, at least you should have 10% or more to see reasonable peaks. So that means if you label with the 57, then you can expect a signature in the EPR spectrum. What signature? Hyperfine signature, a hyperfine coupling signature. So in case of nickel, similar thing. If you cross 10% nickel 61, again you can get. That is why in most of the microorganisms, when they generate the metal enzymes from the microorganisms, they feed the input of the iron salt as the 57 labeled iron salt and the nickel 61 labeled iron salt. Then the proteins that are developed in their body, they are all utilizing the 57 iron, 61 nickel, and that becomes 100%. Then you can get very good EPR signal. Copper is again 3/2, 3/2. So totally, so you can get 100%. You can expect the copper, the coupling. And molybdenum, yes, 5/2, 16%, and then another 5/2, 9.5%. Together is around 25%. So it's very well understandable. So molybdenum case also you will see nice hyperfine coupling. So if you take tungsten, yes, 14% with a half, very good. Now what are the things differing? The value of spin, that will change this. Now that means number of lines coming up. Other is the abundance. So these two together, it will become a signature pattern. Signature pattern. Nothing else will match with that. I have already explained to you such kind of signature pattern, isotopic distribution, when we talked about the mass spectrum. Similarly here, hyperfine signature pattern. Okay, so this is the hyperfine signature pattern, is very unique for that particular thing. So nothing else will match. Now you got, I hope you got the whole exercise. I took it one by one in this, but you need to spend a little time. Now whatever I mentioned, just let us look at. Let's take a case with the values of L +1, 0, -1, 3 of them. So that is, if you put 2 Ni, so 2 into 1 into 1 plus 1, so that is 3, and that's what you find here. The 3 lines are that, and the 3 lines is shown here. If you look at the absorption type of signal, you will get the 3, and if you look at the derivative signal, this is what you get in the spectra nowadays. Okay, to get a feel of what I mentioned now, both for the hyperfine and the super hyperfine, let us start going through that together. So please join me in going through that one by one, details of this, so that you will understand better. Now one electron, nothing is there, just one single line. So if this electron is present in a nucleus, and that nucleus has got I is equal to half, then you have 2 into 1 into half plus 1, that will be 2 lines you will get. And if that unpaired electron is in a nucleus whose I is equal to 1, it will be 2 into 1 into 1 plus 1, 3. And then if it has a 3/2, 2 into 1 into 3/2 plus 1, that will be 4. So you can see that. So that means that unpaired electron is in a nucleus whose I is half, whose I is 0, let us say here, no coupling, I is equal to half, 2 lines, I is equal to 1, 3 lines, I is equal to 3/2, 4 lines. That is hyperfine. So here, if you look at the previous slide, In this table you can see there are things with a 3 by 2, there are things with a half, there are things with a 1, all these kinds of things are there. Okay, so different kinds of nuclei with different kinds of things. So molybdenum 5 by 2, copper 3 by 2, manganese 5 by 2, and the iron of course with very low intensity, low abundance, half. So cobalt 7 over 2. So all of these, but none of these numbers you need to mug, because in any question the I value will be given to you all the time. So don't start mugging the things. Now let's come to the case where you have an electron, unpaired electron, and then that is connected with the two such nuclei with I is equal to half. Two such nuclei, 2 into half plus 1, that will be 2 into 2 such nuclei with I is equal to half. So 2 into 2 into half plus 1, so that will be 3. So you will get the 3 lines in that, and if you have 3 such nuclei neighboring, then it will be 4 lines, 4 nuclei with I is equal to 1. So 4 nuclei, 2 into 4, I is equal to 1 will be 8 plus 1, 9 lines. So you can see all the 9 lines, 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, all 9 lines. Now their intensities, like in the NMR case, so when you have 1 proton splitting into 2, 1 is to 1, 2 protons splitting into 3 lines, 1 is to 2 is to 1. That means first line will be 1 time intensity, the middle line will be double the intensity, the third will be same as the first one. And in case of 4 lines, the first one has certain intensity, the next line will have 3 times intensity, the one next also will have the equal intensity, and then you have a 1 time intensity. This is the kind of thing which you find here as well as even in the NMR also. So in the NMR it is a nuclear spin coupling. Here you are looking at electron spin with the nuclear spin. That is what is called electron nuclear coupling. Okay, so now let us look at one example immediately. There we are going to see many more examples at a later stage. At this juncture, let us look at one example at least. So this particular material can be the diquinone, paradiquinone. If you radiate with X radiation, that will create a radical, anion radical. So anion radical will not sit in the middle, will not sit here, will not sit here, will not sit here, etc. It will be moving entire pi skeleton, it will be moving. So when it comes here, it will interact with this hydrogen. When it comes here, it will interact with this hydrogen, it interacts with this hydrogen, with this hydrogen. So that means that unpaired electron that you have, which is moving on the total pi system, will interact with 1, 2, 3, 4. Are these equivalent? Yes. If you look at this is adjacent to this, this is adjacent to this, adjacent to this. So they are magnetically equivalent. So therefore all these 4 together, so that will be a kind of a isotropic type of a system where all 4 are equal. Therefore the number of lines that you would expect in this are 2 into 4 into, so what is the spin? Hydrogen half, so plus 1, so that is the 5 lines. So you can see all the 5 lines here, 1, 2, 3, 4, 5 lines, you can see 2n plus 1, 2ni plus 1. So, and if you go to a room temperature, if you go to a higher temperature, the lines are sharpened. So that is because there is a very fast kind of a delocalization taking place, so therefore that becomes, lines become very fast, sharp. So that is not important at this moment, but just I have information I gave you. Let us look at some standard molecule that uses in this is the DPPH, diphenyl picryl hydrogyl kind of thing, which is taken as Z is equal to 2.0036 plus or minus 0.002 kind of a thing that you look at that. And this is the molecule, you can see this is used as a spin label in some cases, or standard, or as a reference, all the things. And you can see the structure, it is in this kind of a fashion. Okay, so you can get the isotropic spectrum for this, and when you have an anisotropic environment, you can get all of these as well. So, and their coupling, etc. So this electron can be here, this electron can be here, and all of these. So therefore you can get this corresponding 5 line, 1, 2, 3, 4, 5 line. How do you get 5 line? There's 2 nitrogens are there. There is 2 into 2 nitrogens, and nitrogen has got 1, there is a N is equal to N 15, which has a very high abundance, which is 90 plus abundance or something, plus 1. So 4 plus 1, 5 lines. You can see that number of lines coming is the 5, and that's what you would see this spectrum when you have the completely resolved. Okay, so we have looked at one aspect, that is the electron coupled with the nucleus of the same, the nucleus of the neighbor, which is connected to that, both we have looked at. And then, so one is called the hypophyne, other is called superhypophyne. Now, will there be a coupling between the two electrons? Yes, there can be coupling between the two electrons as well. So how two electrons? It is not a diradical, but a lot of transition metals in their some spin state of the high spin state, they will have 2 electrons, and sometimes even a lower spin state could also have, and these 2 electrons may be weakly connected or maybe not so weakly connected or strongly, or they can be 2 metal ions. So one metal here, another metal here, so 1 electron here, 1 electron here, and these 2 can also be coupled, either the weakly coupled or strongly coupled. So both are possible. So depending upon that, your spectral signature changes. So weakly coupled case, the interaction, so this spin, we are not talking about the nucleus here, we are talking about the 2 spins, the 2 metal ions, or it could be 2 unpaired electrons on the same metal, either of these. So they can be interacting weakly or they can be interacting strongly. The weak interactions are basically coupled through these kind of interactions, through distance based interactions. These are called dipolar interactions, so which are distance oriented in this. So such kind of an exchange can provide, if they get added up, it will become ferromagnetic kind of interaction, the two electrons, magnetic vectors, or antiferromagnetic. Because I have already explained this in the past when I talked about the magnetism aspect of it, so it's nothing new that you all. And such kind of interaction are these one. So we have, so these are with between the 2 spins is a proportional by 1 by r cubed. So this is the where the thing is. So therefore one needs to look at this coupling values in terms of whether they are the positive ferromagnetic, the negative for the antiferromagnetic kind of things, and such interactions can be taken up to 10 to 15 angstroms away from the electron, that distance beyond 15 angstrom, so the effect can be 0, effect of this is 0. So up to 15 angstroms 0. So that means if there are 2 molecules in the lattice, and if they are separated by 5 or 7 or 10 angstroms, and if both are having the unpaired spin, then you can still find certain level of coupling values of that. Now the second one is the strongly coupled. So when you have strongly coupled, and then you know that their spin system will become the total spin is the spin of individual of all this, and this will give 2s plus 1 states, 2s plus 1. So if these 2s plus 1 may also get further broken up. So they in under the normal conditions, when you have a weak coupling, they all have the same energy, all that 2s plus 1. 2s plus 1 could be 3 or 5, whatever it is, and they will have the same energy. But in the case of strongly coupled, these will still further split and there will be energy difference. So once you have energy difference, even in the absence of the external magnetic field, because of the strongly coupled system, even in the ground state of that, you may not have the completely all the 2s plus 1 states are degenerate, partly they will be non-degenerate too. Let's look at that example here straight here, and so you can see if you have a strongly coupled, then out of the 1, 0 and plus 1 minus 1, so the plus 1 minus 1 has come as a doublet and the 0 has come separately. So you see that that is for a strongly coupled. You see that when these two are there, they're strongly coupled, then you can get. Okay, so in the 0 field splitting, we talked about one is for 0, one is for the plus 1, plus or minus 1. When you put the magnetic field, the plus or minus 1 will further split. So, you have plus 1 and minus 1, and you have the 0 also. Now, you have all the transitions occurring. So, similarly here this is for the 5 over 2, we will have plus or minus half, plus or minus 3 by 2, plus or minus 5 over 2. But under the magnetic field, this is in the absence of magnetic field, is known as 0 field splitting. So, strongly coupled electron coupled systems will have partly this non-degeneracy being found even at the without any magnetic field, and applied magnetic field they will all further split, and they will further split 3 by 2, plus 3 by 2, minus 3 by 2, as well as plus half, minus half, plus 5 by 2. So, all this. So, you will get all those corresponding lines, and therefore, you get the corresponding signature quite different in that. So, we have looked at the electron nuclear coupling of the same nucleus where the electron is arising, and a different nucleus which is bound to that, etc. So, we have looked at, and now just now we looked at the electron with another electron coming from the same or coming from a different. So, that means you have to see both of them, one molecule, another molecule farther away by this in a lattice. So, if the distance is greater than 15 angstroms, you can forget about their interaction, they cannot communicate. If they are close by, they can communicate less than 50. And in case of strongly coupled, even in the absence of magnetic field, the ground term of the spin 2s plus 1, certain degeneracy is being lifted. So, therefore, your transitions can happen even in the absence of magnetic field. And of course, when you apply the magnetic field, you will have further. So, you can see, so you can vary the magnetic field and measure the spectrum. That will give a good signature pattern to understand the particular compound. Okay. So, as a function of, so in some of the very detailed cases, people will measure the EPR spectra not at just one magnetic field, at different. I have already told in the previous class, at different magnetic fields, the gigahertz frequency will change, which we call X band, Q band, W band, all these kinds of things I already talked to you. So, you can change the magnetic field strength, that means your power obviously changes. The gigahertz power will also change in this. So, we will start looking at the examples to understand whatever we learned. I think we more or less learned all the basic principles, including the hyperfine and super hyperfine electron coupling and electron nuclear coupling. Now, we are with all the things being the gun being loaded, now we need to really fire with those things. Okay, and then understand the examples better. Thank you very much.